So now let's talk a little bit about the fundamental forces and kind of where they come from, as well as a whole bunch of new particles that we've discovered even in the last 50 years or so. We're pretty familiar with this from Physics 241, and this from Physics 242, and this from Physics 241. And we've talked about how the strong force is going to hold nuclei together a little bit in Physics 243, and it has a mediating particle of a meson. Let's talk about the weak nuclear force. The weak nuclear force is weaker than the gravitational force, or is stronger than the gravitational force, but weaker than the other two fundamental forces. You can kind of see relative strength going up in this direction right here. The weak nuclear force is going to be what holds a neutron together, and it does have a mediating particle. These guys are a new type of particle called bosons, so B-O-S-O-N, and keep in mind that it operates on a really small scale. So it's going to hold neutrons together, but it's not going to do much more than that. These bosons are a new form of particle, and they're actually very short-lived. We discovered them in about the 1980s. Let's talk about some other particles that we've discovered in the last 100 years or so. Once we discovered the positron, we would expect that there's going to be essentially an anti-proton. So this guy right there, mass of essentially going to be just like an anti-proton is, as a positron is to an electron. And when those guys come together, then they can destroy each other and create some energy. And then we're going to be talking about some new particles. We're going to be talking about leptons, which are essentially going to be very light ones, such as electrons. We're going to have the mesons, which we've talked about a little bit. We're going to come back to those, and those are kind of intermediate particles. These guys are pions. And then we're going to have baryons, which are essentially going to be heavy, more massive particles, and these guys are going to be things like nucleons. Now, this classification kind of from light to heavy is kind of useful. However, sometimes it's more useful to talk about these guys in terms of what nuclear force they're using. For example, we could talk about hadrons, which are going to include both mesons and baryons. So these guys right over there, they do have strong nuclear reactions. However, leptons do not have strong nuclear interactions. To make things even more complicated, we have different kind of subclasses. For example, we're going to mention a little bit fermions. And fermions essentially are going to have half-integer spins, and these bosons, these guys right down there, do not. So actually they're kind of interesting, and they also don't obey the Pauli exclusion principle, because they don't have any. So first, let's talk about the light ones. Let's talk about the leptons. And leptons, again, they do not experience the strong nuclear interaction. And these guys also do have half-integer spins, so ms is equal to plus and minus 1/2, and that by definition is going to make them a fermion. Now, there's 6 of them that we know about. We're familiar with the electron, and it does have an antiparticle, as I said. And the mass is going to be this guy right over here, really important. These guys are characterized by 3 lepton numbers, and lepton number does need to be a conserved quantity when we take a look at nuclear reaction. We also have what's called an electron neutrino, something that has no charge, and this essentially is going to be, this means no mass. This is probably the smallest particle that we know about. It's got a symbol right there. It does have an antiparticle. And again, just take a look at that mass. Very small. It does have the same lepton number as an electron, and it is stable. We have muons. I talked about those a little bit earlier. Have their mass right over there. And then we also have another neutrino going along with that guy. Again, small mass. And then we have this lepton right over here, plus and minus. It's got the antiparticle and slightly more massive. You can kind of see how the lepton number tells us whether we're looking at an electron, a muon, or the tau. So as I mentioned on an earlier slide, lepton number has got to be a conserved quantity. And let's just take a look at the lepton numbers for some various decays. So here we are, we're looking at the U+, and it's going to go to a positron, a neutrino, and then an anti-mu neutrino. So this guy right here has a lepton number also be of 0, let's see if this side of the equation checks out. This guy has a -1, this guy has a +1, this guy has 0, so it checks out. Now this lepton number, this guy has a -1. Over here, this guy is going to work itself out to be 0, 0, and -1. So -1 is equal to -1. This guy checks out. We don't have any tau neutrinos in here, so essentially we're saying 0 is equal to 0. And that's actually true for all three of these reactions. Let's consider this reaction right here. Just looking at the chart, we're going to have a 0. That guy's going to be 0. That guy's going to be 0. So that one checks out. This lepton number is 0. On this side, it's going to be a 1. This is going to be -1. So this guy checks out. So this checks out. This checks out. Now let's take a look at this. This is a meson, it's not a lepton, and so all of its lepton numbers are very simply equal to 0. So L sub B is going to be equal to L sub mu, which is going to be equal to L sub tau, which is going to be 0. So we have our 0. This one has 0, this one has -1, this one has +1. So this one does check out. Now, again, at 0, this is going to have a 1, this is going to have a 0, that's going to have a 0. This guy does not check out, this decay is not possible, and we've never observed it. Now, let's move on and talk about hadrons, and the hadrons are going to experience the strong interaction. And as I mentioned, we have mesons and baryons that are kind of subclasses of these guys. I'll show you on the next slide some properties of hadrons. You may have heard of hadron by the Large Hadron Collider. And that's a really big collider where they collide hadrons and all sorts of stuff together. One thing about hadrons is they're going to have some numbers associated with them, and all of these numbers are going to be conserved quantity. So when we take a look at the chart in the next slide, keep in mind if a reaction occurs, much like the lepton number had to be conserved quantity, so also does the baryon number. So I'll come back to this example in a second as soon as I move on right here. So these are some hadrons and their properties, and we have the mesons and the baryons. You can kind of see their mass kind of going in this region right there. So as I said, mesons are kind of intermediate, baryons are the heaviest. These are their charges, and it's all a ratio to the charge of an electron. These guys are fermions. They have spin 1/2. These guys are not fermions. They don't have any spin. And they also have a baryon number, which is given by B. Now, essentially, the baryon number, all baryons are going to have a baryon number of B, but when we take a look at the antiparticles, so if we were to take a look at an antiproton, it's going to have a baryon number of -1, and therefore, if a proton and an antiproton were to come together, the baryon number would be conserved. The same would also be true for an antineutron. It would have a baryon number of -1, and so on and so forth. All these guys are going to have antiparticles that can cancel them out, for lack of a better word. I'll talk a little bit more about strangeness in the next couple of slides. These are the mean lifetimes. You can see that they're really short, and they're going to decay into various things. This one decays into light and so on and so forth. We will come back also and talk about how these hadrons are made up of even smaller particles called quarks in a couple of slides. So let's take a look at just a couple of reactions, flipping back to this example. If we had a neutron and a proton, that would decay into a neutron plus a proton plus a proton and its antiparticle. Is baryon number conserved? It always should be. So again, keep in mind that any antiproton is just going to have a baryon number of -1. So a neutron and a proton are both baryons. Baryon number is going to be 1, so it's going to be 1 plus 1. And then 1 plus 1 plus 1, 1 plus 1 plus 1, and then plus -1, and you can kind of see that, yes, this guy does check out. We have 2 on the left and 2 on the right. Now let's consider this guy right here. That's going to be 1 plus 1, and then 1 plus 1 minus 1 is what it's going to work its way out to be. You can kind of see this guy right here. It's not going to work out. So this one does not conserve baryons, and it's not going to be able to happen. Now, I do want to come back and talk about strangeness a little bit. Turns out in the 1950s, as we were colliding particles, something that we kind of found out about these mesons, the K plus and K minus, is that they were always produced together, and they were produced rather at a very high rate, and that kind of suggested that there should be some strong interaction process. However, their long lifetimes suggested that they should be a weak interaction or a weak process, And so we came up with a new quantum number, strangeness. And as we learn more and more and more about baryons, we were able to kind of categorize them with a strangeness number, and there's really nothing like it in classical physics. Now, strangeness is an interesting creature because it's conserved in strong reactions, but it can change by 0 or 1 in weak interactions. So strangeness, strong means it's going to be conserved, and weak means that it can change by 0 or 1, so 0 to 1. So it can actually change in these types of reactions. Now, let's take a closer look at hadrons. Hadrons are kind of messy. Leptons were pretty straightforward. We only had 6 of them, and we generally believe that these guys are fundamental particles. However, hadrons are actually composed of something that's even smaller than them, and these guys are called quarks. And we originally discovered 3 quarks, but we've discovered a couple more. And let's talk about these quarks. These quarks are each going to essentially have a third of a charge, and they're going to have a third of a baryon number, and they're also going to have half of a spin, and so these quarks are also going to be fermions. And we can say that hadrons are going to be composed of usually 2 to 3 different quarks, depending on their charge and all that. Let's take a look at some hadrons. Let's take a look at a proton. We kind of named these quarks. Originally they were named U, D, and S, and I'll show you what some of their properties on the table. And the U guy is going to have a plus 2/3 of a charge, and the D guy is going to have negative 1/3 of a charge. And when we talk about a proton, we know it's going to have a charge of plus 1/3. So a proton is going to be is going to be comprised of 3 quarks. It's going to be U, U, and D. Probably not surprisingly, the antiproton is going to be constructed from an antiquark, and it's going to be a U, U, D. And anytime we put a bar over a thing, essentially we're just putting a negative sign in front of any of these quantum numbers. You can convince yourself that the neutron and the pion and this guy right over there are comprised of these quarks, where, again, this is an anti-quark, and so we've gone from a from a negative charge to a positive charge. Anytime you see that bar, that's what it means. Now, these quarks, the 3 original quarks, the names U, D, and S, where does that come from? Well, originally it came from up, down, and strange, and we call these actually flavors. And some things about these guys right over there, it allows us to create things. For example, the neutron, we know it has mass, but it doesn't have any charge, but it can be comprised of little quarks that do have some little fractions of charge, as long as the fraction of the charge adds up to 0 to make it a neutron. That's where it gets its mass from. Now, what binds quarks together into the hadrons that we saw on the previous slide is actually going to be some spin 1 bosons called gluons, and these things are massive, or massless, and pretty much this is the same way that photons can mediate the electromagnetic interaction that we saw in physics 242. Now, one thing about quarks is that they are fermions. They have half spin, so for fermions, they have a spin of plus or minus 1/2, and so they must obey the Pauli exclusion principle. And this would seem to, say, hey, we can't have a baryon for having 2 or 3 quarks of the same flavor. However, we did see that on the previous slide. We saw that a proton had a U, and a D. So what's up with that? Well, it turns out that these quarks are going to have a property of them called color, kind of whimsically, actually, and people typically use red, green, and blue, and we can have quarks of different color, say a U, and a D from a proton. We would just say that the quarks have different colors, and typically they're going to be red, blue, and green, the primary colors. Now, color is a conserved quantity, but I'm not going to do too awful much with color. I want you to know that it does exist. Now, after the after the up, down, and spin, we've actually discovered 3 more quarks, and these guys were called charm, top, and bottomness, CB and T. And essentially, as we were colliding more and more things together, and relatively recently, I'm talking in the 50s up to the 1960s, we discovered these new quarks that could create different things. For example, we could have a charmed baryon or something like that. So if we were to just, go to Wikipedia and check out the standard model, which is going to essentially talk about fundamental particles, we have fundamental particles. We've talked about leptons, and as I said, we do believe that these are fundamental particles. Here we have the mass, the charge, and the spin of these guys, and so you can see, electron is going to have a charge of -1, and it's definitely going to have a spin. We've talked about that a lot. And you can convince yourself for all those leptons. Here we have the mass, charge, and spin of the up, down, and the charmed top strange quarks. We also have these gluons, and again, I said these things virtually have no mass and no charge to them, but they do have some spin. And we also have some other fundamental particles. We have these W and Z bosons, which I said are going to mediate the weak nuclear force. One thing that's kind of interesting is we do have some particles that the book doesn't talk about, and I don't have necessarily time to talk about it. We do have something called the Higgs boson that was actually found after this book was created. And something else I found on Wikipedia is that a fundamental particle is going to be a magnetic monopole. Hypothetically, it should exist. At least that's what string theory predicts. Kind of interesting. To date, we've found about 61 elementary particles. So matter is made up of a whole bunch of different things, and I do predict we will see more and more and more of them. So this table right here does have the properties of the 6 quarks, and again, the charge is always going to go by 1/3, the spin is always going to go by 1/2, the baryon number is going to go by 1/3, and then the next 4 guys, strangeness, charm, bottomness, and topness, is going to go by ±1. And here are the symbols, U, D, and S we talked about, on charm, bottom, and top. And again, anytime you see a U bar, we're essentially just going across the board, putting a negative sign on this, and it's going to allow us to create antiparticles that are the exact opposite, quark-wise, of the original component. So that's how we can create antiparticles. One thing to kind of keep in mind is when we create particles, we can't just create a particle with, like, 2/3 of a spin or something like that. So a particle that was comprised of just 2 quarks, a U and a D, let's take a look at the charge. U is going to have 2/3, that's going to have a -1/3. This particle that I just kind of whipped up would have a charge of 1/3 that of an electron, and that's going to be impossible. So, spin's always going to go by 1/2. We're always going to need baryons adding up to 1. These guys will always add up to 1, but we do have to be careful when we create particles. We can't just randomly throw stuff together. The baryons and the charge definitely have to add up. Okay, now that was enough crazy stuff. That was enough particle physics. Now let's kind of finish off by talking about cosmology, which is actually going to be related to the strong, weak nuclear forces as well as gravitational. Something that we have noticed is that the universe is expanding, and how do we know that? Is it turns out that there's a red shift of light from distant galaxies, and it's always red, and that means that these galaxies are moving away from us. What we can do is we can kind of go back and revisit chapter 37. We talked about the shifting of light due to its speed, and we could actually go ahead and write the wavelength that the light is going to be shifted, and that's related to the wavelength of the galaxy as well as the speed of light. So that's kind of the original wavelength, that's the shifted one, and the speed of light plus the velocity, speed of light minus the velocity. We could also write this in the language of the speed if we do, for example, that we were looking at some spectral line and we knew that it was shifted by a certain amount, then we could figure out how fast the galaxy was moving away from us. Now, a fellow by the name of Hubble actually noticed that there was a kind of a linear relationship between how far away a galaxy was as well as its speed. He kind of said, it's going to go kind of like this, and he came up with a directly proportional relationship. Said that the speed is going to be equal to a constant that was named after him, Hubble's constant, multiplied by the distance. Now, the only thing about this equation right here is that the units are, a little bit funky, and when we talk about distances in space, we're talking about really, really, really long distances. Very often, you'll see them in parsecs or megaparsecs, so MPC, and that's times 10 to the 6 parsecs. And that's actually 3.26 light years, and we may also see this in the language of like megalight years or something, and that's how far light can travel in a year. Now, that's a long way. Remember, light travels at 3 times 10 to the 8th meters per second, and a year is a whole lot of seconds. One light year is going to be 10 to the 12th, almost 10 to the 13th kilometers. Really long way. Hubble's constant in seconds is this number right over here, and it says, the book says that's within about 5%. Very often it's expressed in a more funky unit. It's going to be expressed in kilometers per second per megaparsec. Hubble's law is really straightforward. Just pay attention to the units as we go ahead and play with it. Let's take a quick look at example 44.8. I just realized I misspoke on the previous slide, so pay a little bit more attention to this slide. If we were to be looking at the spectral lines coming from some constellation that's really far away, actually they picked one in Ursa Major. Credit for Wikipedia, got the bear right here, kind of see it. This is the wavelength of the source. I misspoke on the earlier slide. We know that calcium is going to have a line around 393, and if we observe it redshifted, it's say at a higher wavelength, so it can be 414 nanometers. What speed is the galaxy going away from us for? Pretty straightforward. We take the ratio of 414 to 393 and see that it's been shifted up by about 5.3%, and we can calculate the velocity to be this velocity right there. We can then follow example 44.9, and let's just figure out how far away that guy is. So what that guy is equal to what? Again, really straightforward, really easy to use. Just pay attention to units. So what we have to do is we have to realize that we have our speed in meters per second. We definitely want to reflect that. So what we can do is we can just take Hubble's constant and very simply convert the kilometers per second into meters per second, so times 10 to the 3, and that's still per megaparsec. We can rearrange it, have our speed right up there, have this guy right over there, kind of see meters per second goes away, and we're left with 220 megaparsecs. Let's express this a few other ways. We could express that in the language of parsecs, light years, or meters, and that's a really far way away.